Okay, so we've been using kinematic equations for the first part of this course, and now we're thinking of using W equals delta K, and we want to sort of compare these two techniques, show that they are consistent, and by that I simply mean that if we have, say, a force in the x direction, then by F equals ma, we have an acceleration in the x direction. And the kinematic equations are, of course, still true. And from the perspective of work equals delta K, it must be true that, right, the work, if the force is a constant and the acceleration therefore is constant, then we have fx in dx, and that ends up being fx times some, let's say we go from x naught to x, so this is sort of some prime variable. So this becomes x minus x naught as the work that is done by this force in the x direction. And it must be true by W equals delta K that this is 1/2 m v, say, final, vx final squared minus 1/2 m v x initial, or just v naught squared. So let's just leave it as v naught x. Okay, so we can get this expression from the kinematic equation. So let's look at the kinematic equations, right? It's x minus x naught equals v naught xt plus 1/2 ax t squared, and vx equals v naught x plus axt. And this idea has no explicit mention of time, and so we should be able to recover this from this if we can get rid of the time variable. So from this equation, we can see that we can get the axt term in terms of vx and v naught x, and then we'll plug this into here. Let's see. And then, we can also plug it into here. This is the time, so that this term here will be vx minus v naught x over ax. So we'll get rid of the two times here. So this equation becomes x minus x naught equals v naught x times t, and the t here is vx minus v naught x over ax from this, plus 1/2 ax times t squared, so that is the same t here. So we're going to square this quantity, vx minus v naught x over ax, and here therefore we get x minus x naught is equal to v naught x times vx minus v naught x squared. This is all over ax plus, I'm going to get 2ax here because of one factor of ax there, and I have vx squared plus v naught x squared minus 2 vx v naught x, and so this becomes x minus x naught is equal to, let's see, I have so I have v naught, sorry, I want to multiply this by 2. So let's multiply this by 2 v naught x minus 2 v naught x squared over 2ax, so that I have 2ax here. And now I have see, Vx squared, I have no other Vx squared, so I have Vx squared. Got rid of this term. I have V naught x squared minus 2 V naught x squared. So that's minus V naught x squared. So I've gotten rid of this and this. And now I have 2 V naught x Vx minus 2 V naught x Vx. So that goes away. And this is all I have left. So what I have here is that ax times x minus x naught is equal to Vx minus V naught x squared over 2. And if I multiply by the mass, I get max times x minus x naught equals Vx squared minus V naught x squared over 2 times, well, I'm going to put the mass here. So let me erase this a little bit. Let's put the mass here, and so I can see that this is the difference in kinetic energy, and then via F equals ma, I can write this as Fx for this times x minus x naught is equal to m Vx squared over 2 minus m times the initial. Right, so this is just delta k, and indeed I have recovered that expression.